right, so I basically created two waves on the computer. Right. Besides one being blue and one being purple, they are not the same. If you'll notice, they both start in the same spot, basically at 0, 0. They both have an amplitude of 1, but this one ends on the way down, and this one ends after it's gone down and it's coming back up. Now, probably not many of you can notice the difference really between them, other than the fact that at the very end, they end at a slightly different spot. So I then took, I think it was the purple one, took the blue one, I took the blue one and basically traced it onto the plastic, and just showing that they line up. So you can see lines that mimic the blue. Now I'm going to put the purple one with the line I traced. And here it's a little bit clearer the fact that they don't line up. Even though they start out somewhat synchronized to start with, by the time they get over here, they're clearly out of sync. And then I just added them together. Because when you have two waves on top of each other, in essence, what you're doing is just adding them. Which is why constructive interference, when they were on the same side, because they both had the same, say, positive values, and destructive interference when they were on opposite sides, because one's a positive side and one's a negative side. And if you add them together, you get this. So they start out with an amplitude of around 2, and then it slowly gets less and less as becomes less constructive. Now officially, I think we're above 1 the entire time, so this is still officially constructive interference, at least at the peaks here. So then I extended it. To extend it, you get this, where clearly we've got constructive interference to start with, and then by the time here, it's completely destructive. So we can mimic this with sound. All right, that's clearly 440 hertz. What's happening when I say 440 hertz is that the pressure wave is, we have basically the speaker on that is oscillating back and forth 440 times a second. That pressure wave will eventually hit your ear and make your eardrum vibrate back and forth 440 times a second. If you are tone deaf, it'll all sound the same to you. So let me play a different one. This is 439.5. 440. Can anyone hear the difference?
Is one kind of lower than the other?
One should be slightly. So you think you might hear it?
I just guessed. I think I heard it, but I'm not sure.
Here's the higher frequency. Here's the lower frequency.
Sounds the same.
What's that?
I think it sounds the same.
Yeah, some people have a sensitive enough ear. I do not. They sound the same to me. However, there is a difference between them. Because if I play them at the same time, I'll start with the 439.5, and here's the 440. So we have what is known as a beat frequency. The fact that you get it was even louder to start with, and then it died off to almost nothing. So here's the math behind it. We had 440 hertz and 439.5 hertz. The beat frequency is, here's the sophisticated math, 0.5 hertz. Because that is my beat frequency, beat, it has a beat period. What's the relationship between period and frequency?
Frequency is 1 over period and vice versa.
So the period would be 1 over 0.5, which is 2 seconds. So now we can test out if that actually is holding true here, because it should die off every 2 seconds. I'll do sophisticated math, or this sophisticated timing here by counting. 1001, 1002, 1001, 1002, 1001, 1002. Is your watch matching it?
Yeah.
Right. So every 2 seconds, it dies off. So it has, the beat has a 2-second period. Now, human hearing has an upper threshold. There are not many people who can hear above 20,000 hertz. I can't hear above 17,000, somewhere around there. Actually, I have tinnitus, and so between 8 and 10,000, I lose out, and then it comes back, and then somewhere around 17,000, I can't hear anymore, and that's just age. So 20,000 hertz is sort of the upper limit of what humans can hear. I'm sure there's some people who can do higher than that, and older people won't, but there's a textbook that used for one of the other classes that talks about if you did a 23,000 hertz sound, which you can't hear, and a 22,500 hertz signal, the beat frequency would be 500 hertz. And so the textbook claimed that you should be able to hear the two of them played simultaneously. Good luck finding software that does that, but it did find some software that would play things in the ultrasonic range, and I couldn't hear it. And so I don't know whether that was my hearing or whether it was an issue of the speaker couldn't handle it. So I'm trying to find something to give me conclusive evidence one way or the other than the claim of this book, other claims which I find questionable. All right. Red tube. And somewhere around here, there's a pink tube that actually belongs to the school. So what we're going to do is we're going to make a prediction of what that sound is. And that one, and that one, and that one. So before we get into the two open ends, let's start with the two closed ends. So if I have a string that basically is attached at two fixed ends, let me do that sideways. The string is attached at two fixed ends with a distance L between them. And I want to get the string vibrating so that I am in the first harmonic. The first harmonic basically looks like that. It's the first harmonic. And so this is typically the way it's drawn we have nodes here. This is the node. This is the node. This is the antinode. Now, I'm not claiming that this is in two places at once. This is just the point where it's vibrating the most. And then the nodes where it's not vibrating at all. The question is, how many waves is this? Now, a wave, typically, if you think about a cosine wave or a sine wave goes up, down, and then back up. That's a sine wave. If this were a harmonic, these would be the antinodes, and then we have a node here, here, and here. So we've got the 3 nodes, 2 antinodes. So this is one wave. So therefore, how many waves is this?
Is it a half?
Is indeed. So L is equal to a half of a wave, or the wavelength is equal to 2 times L. This scenario here is going to be more relevant for the lab that you do on Tuesday. The second harmonic is the next simplest one. I know that the 2 ends have to be nodes because this is, we write it explicitly, 2 fixed ends. So I got 3 nodes. Each time I add a node and an antinode. Or each time I add a half wave. So how many waves is this?
1.
L is equal to 1 wavelength, or the wavelength just equal to L. The third harmonic will wind up better than that, but it's just at some point it's that difficulty drawing down like that. How many waves is this?
1.5.
And as mentioned before, I add a half wave each time. So L is equal to 3/2 of a wave, or the wavelength is equal to 2/3 L. So if you have the wavelength here, and if you knew the frequency, such as in the lab on Tuesday where the frequency will be 60 hertz, you could then predict what the speed of the wave is. Questions are here, because I'm about to do the one fixed, one free. One fixed, one free. Now a fixed end is going to be a node. A free end will be an antinode. So the simplest version I have here is basically that. I got one fixed, one free end, or one node and one antinode. Then the question is, how many waves is that?
A quarter.
Yep. So my first harmonic, this is the first harmonic. I have L, make that distance L, is equal to 1/4 of a wave. Or the wavelength is equal to 4 times L. The next simplest harmonic I can do, again, I have to have a node at one end and an antinode at the other. So the next simplest one basically looks like a fish. How many waves is that?
3/4.
Yep. You add a half wave every single time. So it's 3/4 of a wave, or the wavelength is equal to 4/3 times L. And I do want to point out, this is, I think I've corrected the videos. It's possible I have not. This actually is the third harmonic. There is no second harmonic here. basically what do you multiply the first one by to get the next one. If I did multiply this by 2, I'd have half a wave, but then I wouldn't have one fixed, one free end. So that's why this is officially the third harmonic. This is also sometimes just called the first overtone. This would also be the first overtone over here. Second overtone, so on. And the next one, without drawing the picture. While you're thinking about how many wavelengths the next one will be. All right, what's the next one?
One wavelength.
So if I start with a node and I do one wavelength, I'm going to end on a node.
So 1 1/4.
1 1/4. The reason why I didn't feel like I needed to draw it, and apparently we're in different places right now, but you add a half wave every time. So if I start with a quarter and I add a half, I get 3/4. If I add a half, I get 5/4. Add a half, I get 7/4. I basically get the odd quarters. This is 5/4 of a wavelength. So I'm going to do a full wavelength plus another quarter. And so all right, so let's make some predictions with this. And I don't know if that's the peanut butter jar I just had in my hand, but that's what I have now. I'm going to get some water, and we'll see what it sounds like. So I'm going to put water into, again, hope it's not the broken one. I'm going to put water into the side over here. Water is going to start going through the tube and then into this tube over here. So water is just basically going to funnel through. It'll move until the water levels are the same on both sides. That's a consequence of equalizing the air pressure. Not leaking yet, so I'm feeling comfortable. Notice the water levels rising here as it falls over here. All right, so while that's reaching equilibrium, so basically, the tuning forks, you can tell the newer ones from the older ones because the newer ones have dings all over them. Now, when you're hitting a tuning fork, please do not bang metal on metal. That's why you've got these little marks all along the side here. Now, yes, sometimes it happens, but try to hit it with the rubber stoppers. Can everyone hear that? If I put it over here, basically the sound waves are coming down, bouncing off the surface here, and coming back up. This is the free end. Where the water is the fixed end. This is 512 hertz. You can tell just by the sound. Sounds like about 512?
Yeah, sure.
Yeah, spot on. So my frequency is 512 hertz. You need to figure out what wavelength that is. As soon as I hit this thing, that means this thing is vibrating back and forth 512 times a second. Can't really see it moving back and forth, but well, you should be able to hear it now. Where you get that stutter right there, that's because it's vibrating back and forth. So the speed of the sound is basically the speed of sound. And the speed of sound is approximately, it is temperature dependent, but it's approximately 343 meters per second. Ish. Give or take a couple of meters per second. And so from this, I should be able to calculate the wavelength, because for a classic wave, speed is equal to frequency times the wavelength. So the wavelength is equal to the speed divided by the frequency. So 343 divided by 512. That's meters per second over hertz. And what is the wavelength?
That's 0.66992.
0.66992 units?
So that's
No, not for wavelength.
Meters?
Yep, meters. The hertz, basically, hertz is a 1 over seconds, and so that 1